Most coding interviews start with an array problem. If you default to writing a nested loop that runs in O of n squared time, you likely will not get the offer. The candidates who get hired are the ones who can look at that exact same prompt and solve it in a single pass. This flowchart represents a different way to prepare. Instead of memorizing hundreds of specific LeetCode solutions, you build a mental machine that translates problem descriptions into optimized structures based on their specific constraints. It starts by reading the problem statement and filtering it through a series of exact questions. Under the stress of a real interview, trying to recall a specific block of code from memory usually fails. A categorized decision framework gives you a reliable process to follow. You answer a sequence of questions, and the correct optimal approach naturally falls out. First, ask, do I need fast lookup, pair matching, or frequency counting? If yes, use a hash map. Scanning the array, we store elements in a map. To find a matching pair, we just check the map. That's an O of 1 lookup. Whenever repeated searching slows your code down, trading a little extra memory to build a hash map removes an entire nested loop from your time complexity. If lookup is not the bottleneck, you move to the second question. Is the array sorted and asking for pairs, or do I need to modify the array in place without using extra memory? For sorted pairs, use opposite direction 2 pointers. Pointers start at both ends, moving inward to eliminate candidates based on sums. For in-place modifications, use same direction pointers. A slow pointer guards valid data, while a fast pointer scouts ahead and swaps matching elements back. When strict spatial constraints prevent you from using hash maps or auxiliary arrays, 2 pointers give you a structural way to achieve linear time optimization. The third question tests for continuous ranges. If the problem asks to evaluate a longest, shortest, or fixed continuous subarray, you are looking at the sliding window pattern. Sliding windows expand right and shrink left. Update longest windows outside the shrink loop and shortest inside. But introduce a negative number and the logic breaks. Shrinking might increase the sum. Negative numbers demand a prefix sum array to pre-compute cumulative totals instead. Recognizing negative number constraints stops you from wasting 20 minutes debugging a sliding window solution that is structurally incapable of solving the problem. Let's test this framework. Read this prompt. Find the total number of continuous subarrays whose sum equals k inside an unsorted array that includes negative numbers. Pause the video and identify the 2 specific patterns required to solve this. Real interview questions at large tech companies rarely rely on just one basic tool. Your ability to cross-reference constraints to find the right combination of patterns determines whether your solution passes the technical screen. To solve that problem, you need to combine prefix sums with a hash map. This animation shows the 2 patterns working together. You calculate the prefix sum on the fly to track the contiguous ranges, which cleanly handles the negative numbers. At the exact same time, you store those running totals in a hash map. This gives you instant, constant-time complement lookups for the target value k. By identifying the trigger words independently, an intimidating O of n solution reduces down to just 2 basic patterns stacked on top of each other. Before writing a single line of code, run through the mental checklist. Check for fast lookup needs, sorting or in-place constraints, contiguous window requirements, and the presence of negative numbers. This chart maps trigger words from problem statements, like longest substring or remove duplicates in place, directly to their optimized templates. Take a screenshot of this frame. Mastering this decision framework removes the anxiety of guessing solutions from scratch. You simply analyze the constraints, select the exact tools required, and methodically deploy the optimal strategy.